just as our data values can be discrete numerical or continuous numerical, our distributions can reflect that same behavior. If I, instead of asking you to flip a coin, ask you to take it out and throw it, well then, I can measure from where you're standing to how far the coin went, right? And that's a distance I can measure with any level of precision I want. So instead of being a discrete idea there, that becomes a continuous idea. So if we have a measurement, we are more likely to be looking at a continuous variable rather than a discrete variable. In this case, if I think about a measurement, the chance that you will hit an exact number is really not useful here, is it? We're going to toss a coin across the room. I want to know how far it went. What is the chance that coin traveled exactly 2.137 meters? Infinitesimal, right? But I could say between 2 and 2.1 meters, right? I could say between 2.1 and 2.15. I could give ranges. It's much easier to do ranges for continuous behavior than to do an actual value. In more precise terms, if I really wanted to go through why does it make no sense to talk about exactly equal to a single value, I'd have to do quite a bit of calculus explanation to you. And if you haven't taken calculus, you'll be looking at me like, what the man? So it's not worth it at this point. But the real meat under this idea are some ideas from calculus. That if I want to think about what we were doing on Monday with our probability distribution table, what we were really doing was looking at a histogram. Only instead of counting numbers of events, we counted probabilities of events. Remember our coin flipping idea? Chance of 0 heads was 1 out of 8. Chance of 1 head was 3 out of 8. 2 heads, 3 out of 8. That's a histogram, 1, 3, 3, 1. We just divided everything by 8 to make them probabilities instead. So I can think of a histogram, and if you look at our table for our binomial probabilities, there's a histogram. And those histograms are bigger in the middle than they are on the end. Well, that makes sense. If I want never going to happen or always going to happen, those should be rare when I'm doing something more than once. I do something 3 times, well, maybe I'll get 1 or 2 more often. I'm doing something 10 times, maybe I'll get 3, 4, 5 more often. This is actually a very particular picture. But that general idea of looking at that sort of a graph is what I want to think about when I start thinking about continuous ideas. I'm going to use a PDF, but instead of looking at it like a histogram, it's going to look like a graph. Now, the problem is what those actual functions look like is gross. But let's think about the rules we had for our probabilities. I want to think about this graph as representing the probability at each value of x. But I just said it was hard to think of what was going on for each value of x. Instead, we should think about what's going on for ranges. So I have some function. And I think of the values that I could get for our random variable x. And those will be values down here on the x-axis, right? And I want this point to represent the chance that x is equal to x0. But that's really a very weird idea, that number being there. If this is a PDF, that's what it should look like. Some graph, and the chance of being whatever that value is the y value on that graph, right? That's what our histogram told us, only they were discrete categories. Now it's a continuous idea, so we can take on any value in that section of the graph. I know something about this idea. All the probabilities added up should be equal to what? 1. But the probabilities were the heights in our histogram, right? And if I think about adding those up, I think about adding the area of all those little rectangles. I don't know, rectangles. The problem in going from here to here is exactly what calculus was built for. If you haven't ever taken a calculus class, I'm about to say some words you're never going to hear anywhere else again. If you have taken a calculus class, great. If you're taking one, you'll see it in chapter 5. I want to take the area under this curve. That's an integral. And if I add up all the area under this curve, that should be 1. Because that's what a probability should be. The probability something's going to happen has to be 100%. But then I can think of the probability between two values. I'm making up two spots here, A and B, right? If I think about what we were doing in the discrete case, I was asking, out of the total number of options, how many fell in this category? What I'm thinking about here is, out of this total area, how much of it is in here? Hang on, Leo. Now, there are exact methods in calculus that allow me to figure this out, depending on what I know about the function. But this also helps me understand why the chance of getting exactly one value isn't really helpful here. Think about this one value. If I'm only looking at one value, that is an infinitely tiny, thin line, isn't it? And it's going to cover no area. So the chance of hitting one exact number is 0. But the chance of hitting a range of numbers, that's a shaded area. And in calculus, we do some sort of definite integral. Yes, that's a very long, elongated looking squiggle there. It's designed to look like a long letter S. There it is on the cover of the calc. Like the hole in a violin. Okay. I'm not going to ask you to do calculus. All of the calculus we need to do is going to be replaced by either simple algebra or more tables or software, which will do it for us. But our ideas will still work as long as I can figure out what the graph looks like. I should still be able to say, this is what we get. I think of the area under a curve as a sum of a bunch of rectangles. That's the same as our idea for discrete probability. The chance of it being between 9 and 12, take the 9 and the 10 and the 11 and the 12 and add them all up. Well, the chance of being between A and B, I should draw little rectangles in there and I should do this integral for the area. And that's the calculus part. I'll just shove it into a computer and let the computer tell me what the answer is. But I can do that. As long as the function itself, all of the values are always positive, because you can't have a chance of negative something, right? And that the total area is 1. Here is a function. I would like you to graph this function. I know it's a stats class, not an algebra class. I haven't done this since algebra. That's okay. It's an easy function. Easier. Once we've drawn a picture, I want to be able to answer the question, is this function a probability function? But let's think about this. If I were to graph this, it's 0 everywhere except here. So only between 0 and 4 do I have any y values at all. Everything else is 0. And the y value between 0 and 4 is always 1/4. And it's 0 outside that. So that's the whole thing. That's the whole graph. Everywhere else, this is 0. All the y values are positive, yes? Except for the zeros. They're never negative. That's good. Total area.
We do 1 because it's 4 times a fourth.
Length times width, it's a box. Area is 1. This is a probability distribution function, a PDF, just like we were looking at before. I could use this to create a CDF, a cumulative distribution function, by asking how much area do we cover as we go across, right? And if I did a CDF, if I built a CDF for this function, it would look like this. Think about this. If I am at 0, how much of the area have I covered in our box? I haven't covered any area. But as I move over, I'm going to cover more and more and more and more, right? By the time I get to the end, I'll have covered all of it. And that's a horizontal line, so the amount of area is going to grow at the same rate all the way through. But that means if I can figure out the equation for this, and because I have the equation for that, I can give you a CDF function that we can use the same way we were using our PDF tables. This idea of moving from a discrete picture to a continuous picture is one of the foundational ideas behind calculus. That things don't jump from spot to spot to spot, that they move smoothly. By the way, that's about 300 years of bitching and complaining from one science person to another, arguing over this stuff. No, that's wrong. It's about 2,000 years. Back in ancient Greece, a guy by the name of Zeno of Eritrea, I think. Zeno said, if you want to move from point A to point B, first you have to get halfway there. But if you want to move from 0 to halfway there, first you have to get halfway there. First you have to get halfway there, halfway. You're never going to get anywhere. Nothing moves. It's all an illusion. Somebody threw a tomato at it and said, did it hit you? It's a great philosophy idea. It's absolute bull. But Zeno's paradox is still there. It's still there. We have to be able to divide time up into such small little ideas that we can actually make sense of motion continuously. And that's the idea. We were able to get an average and a standard deviation from our distributions, right? And we were able to say, oh, the average is based on how much is at each spot. We took the value and multiplied by the chance, the value and multiplied by the chance, the value, and then we add it all up. But I don't have just one spot for, I got all this area stuff, right? The ideas work exactly the same. Our average our expected value still works in calculus terms. So does our variance. And standard deviation. Yes, sir.
Sorry, what does that say?
We can still do. Wow. Okay. I'm rushing and therefore can't write properly. Sorry about that. We can still do the average. We can still do the standard deviation, the variance. There are, again, calculus-based formulas for these. They're in the textbook at the bottom of page 234. I just want to show them to you. We're not actually going to do them. But you notice over here on the right, there's our discrete version. Our discrete version says you take the value and multiply by the probability and add them all up. Well, this adding up is our definite integral. in calculus terms. Here, we're doing the average minus each, taken away from each value squared, multiplying by the chance and adding them all up. Average taken away from each value squared, multiplied by the value, add them all up. It's the exact same idea, but calculus is hard. I'm not going to do the calculus, but I can. I will also tell you that these same ideas have interpretations outside of statistics. These are called first moment and second moment. They have physics interpretations. They have biology applications. They have chemistry applications. They have finance applications. There's a lot of stuff here. In more general statistics terms, outside of variance, we talk about kurtosis. You should have heard about that in the DT 100 class. Another idea, different kind of moment. But we can build this up. And that means that our distribution graphs tell us the same sort of things today that we had on Monday. As a matter of fact, that picture looks really familiar. Go back to Monday. We talked about a distribution like that on Monday, didn't we? Yeah.
It looks like it's this one thing here, this picture here, that has this 1 over b minus a plus 1.
Our discrete uniform distribution. So I want to use this idea to create a uniform distribution that's continuous. Now, a continuous distribution is exactly this. It is a constant uniform behavior. It's the same everywhere. But now, I don't have to count the individual bits. Let's think about the graph that we were drawing. Let's say I want to go from A to B. And I want to have a horizontal line here. By the way, in this case, A and B are both positive. That is not a requirement. But let's think about this picture for a minute. I want to make sure the rules still apply. The area of that box is still 1. The area of that box is 1. How long is it? Well, the length is right up there, isn't it? Goes from A to B. So the length of this box is B minus A. There's no plus 1. Because I'm not counting the end category. I'm measuring a length. How tall is it? I want the total area to be 1. And area is length times height. So the height is going to be 1 over B minus A. Hey, wait a minute. Go back and look at the example I just showed you. We went from 0 to 4 and the height was a quarter. Just secondly. That's the formula for a uniform distribution. Yes, sir.
You wouldn't plus 1 on the 1
Because I'm not counting a category here. I'm measuring the distance. That's the whole reason we changed away from that 0.1, that plus 1. Because the plus 1 came from I had to count this end, I had to count this end. Now I just have to measure in between them. And that means that I am required to say this is continuous or this is discrete when I'm talking about a uniform distribution because they give me two different results. Leo, you had a question as well?
So would the B part be 5 and maybe 4, maybe 1 for 8, so that could be 4 times quarter.
Exactly, but it could be, it could be 20 to 60 again, right?
Yeah.
But in this case, I wouldn't have 41, I'd be having 40, because I'm not counting them as different categories. I'm saying we're gonna measure between 20 and 60. So I would have a length of 40. Okay. This is only useful if I think every single outcome is equally likely. Because that's what that distribution shows me. Every single possible behavior is just as likely to happen, isn't it? That's a rare occurrence, but it is possible. This is a big assumption, but it may or may not be verified by our data collection. Hang on a second. When I did the uniform stuff on Monday, I was able to say we should have an average. We should have a standard deviation, right? I should be able to do the same thing here. There's a lot of calculus involved. No, to hell with it. Let's not do any calculus. We'll do the exact same thing we did on Monday. If I want to balance this strip on my finger, I should put my finger in the middle, shouldn't I? So the average, the expected value, is the middle. If everything is equally likely, right in the middle. Our standard deviation. Okay, this is the one where I promise you it is doable with the calculus, but you're going to have to trust me because I don't want to do calculus for you. Blech. That standard deviation is different than the standard deviation from Monday. In exactly the same way that the y value in our function is different from the function on Monday. The standard deviation on Monday said b minus a plus 1 squared. That's the only difference I'm going to see between the uniform continuous case and the uniform discrete case, is whether or not that plus 1 is floating around biting me in the ass. By the way, I can give you the formula for the CDF as well. Because I can draw the picture of the CDF. Let's think about this for a minute. The CDF is going to have a value of 0 at A. Because I will have covered nothing up to here, right? But by the time I get to B, I will have covered everything. And it's growing at a constant rate, yes? That makes that equation a straight line. You know how to get the equation of a straight line, right? Especially when you've got 2 points. You've got the point A0 and the point B1. You could build the equation of this line. Its slope is change in y over change in x and then if I use the point slope form of a line, I get y minus 0 equals slope times x minus a. Hey, wait a minute, this right-hand side is, the left-hand side is just y. I get to say the same thing again. That's the same CDF as Monday, except it's missing the plus ones. It's a straight frickin' line. Top of page 236. PDF formula, CDF formula, mean, standard deviation, command in Excel. Now, let's put it to use. Problem number 9. The actual arrival time of the scheduled 10:20 a.m. bus at Alpine and Broadway is uniformly distributed with time ranging from 10:18 to 10:23. When should the bus actually arrive? On average. That's the first question. What is the average arrival time? The bus is scheduled for 10:20, but if we're uniformly distributed between 10:18 and 10:23, I need the middle. What is the middle? Halfway between those. Hang on. It's a 5-minute window, right? Half of 5 is 2.5. Should be 10:18 plus 2.5, or 10:20 and a half. So the bus is, on average, running 30 seconds late. What's the standard deviation? I have a formula for standard deviation. I can plug in B minus A, that's going to be 5 minutes, square it, 25. Grab your calculator, 25 divided by 12, and then take the square root.
Like 1.4433.
Yeah, 1.4 minutes. What's the chance the bus is early? Hang on a second. That's actually this idea, right? What's the chance the bus shows up between 10:20 and 10:18? So I'm going from one end to a given point. That's a cumulative idea. I don't like using this picture to do that. I like using this picture to do that. So here's what I'm going to think about. I have that, right? From 10:18 to 10:23. What is the height of that box? Hang on. People are thinking. Want to let them do it. Whole area of that box is 1. It's 5 wide. So the height is 1/5. Now, what bothers me is the units there, because that is in time, right? So that's in minutes. This is in 1 over minutes. That's a weird unit. That's okay. I asked, what is the chance between 10:18 and 10:20? All I need to know is the area of the shaded box. That's all I need. Well, I know the height. The height is 1/5. How wide's the box?
2 minutes.
2 times 1/5. The chance is 2/5.
So 40%.
0.4. Now, the other way to think of that is to think of this formula up here for the CDF, right? If I think of the CDF, I could say, well, it'll be 1020 minus 1018, that's 2 minutes, over 1023 minus 1018, that's 5 minutes. Don't I get exactly the same fraction, 2 out of 5? Do I need the CDF? No, and the less crap I have to memorize, the happier I am. As long as I can remember, what I really want to do is draw this picture. Now, by the way, this is the chance the bus is early. Without doing another picture, what's the chance the bus is late? 1 minus 2/5, the other area. It's the rest of it. 3/5. I could, yes.
If the bus arrived at 10:20, wouldn't that mean it's on time?
Which is remarkable, isn't it? Like we said, on average, the bus is arriving at 10:20 and a half, isn't it? And yes, if it arrives on time at 10:20, but the chance of it arriving exactly at 10:20 would be a box that has no area, isn't it? It might arrive a little early, a little late. What's the chance it actually arrives at exactly 10:20:00? 0.00. That's actually, again, a calculus trick. The chance of any exact value happening is 0. So I could just as easily, you notice I used less than or equal to here. I could just as easily say, what is the chance that the bus arrives between those two? That's the same value, because there's no area on each end. So whether we use less than or equal to doesn't matter. More questions? You look like you want to ask me something.
No,
Okay. I use this idea as a building block because this is basically the same as what we did Monday. But when I start trying to take my binomial idea and move this from discrete to continuous, I end up with a lot more complicated set of expressions. Carl Friedrich Gauss developed this idea, and it's called after him a Gaussian distribution, but it gets used so much that we call it the normal distribution. This is the most common distribution out there. And we will use it basically for the rest of the term as the basis for everything else we're going to keep doing. The Gaussian distribution is defined in terms of its mean and its standard deviation. But think about this picture. That's the picture for our histogram for our binomial distribution. I started to say Bernoulli. I'm like, no, that's the guy's name. Binomial distribution. When I smooth that out, I get this picture. You've seen this. Zach, you're nodding at me. Where have you seen it? Oh yeah, it's an evil thing. It's on a test, yes. But this is what everybody thinks of when you talk about a bell curve. That's the bell shape. It's defined by its average and its standard deviation. The average tells me where the middle of this curve is. The standard deviation tells me how wide it is. So this picture is our normal distribution, but it's determined by its average and its standard deviation. So I'm going to end up with a curve, and here's where I get to be a crappy artist, whose middle is our average, and whose width is determined by its standard deviation. If the standard deviation is big, then we'll have a wide curve. If the standard deviation is small, we'll get a very narrow curve. But they'll all have roughly the same shape. They'll all have this same sort of picture. For all intents and purposes, I really only need to care about the values that are within 3 standard deviations. Once you get outside of 3 standard deviations, 3 above or 3 below, this graph is so close to the x-axis that it's basically invisible. So most of the weight, the area, is going to be between 3 standard deviations on the low end and 3 standard deviations on the high end. Mu minus 3 sigma or mu plus 3 sigma. That's most of it. Now, I will tell you that there is a formula for this curve that I will also tell you I have never used my entire blessed life. Page 238, there's the same table that we saw for the uniform distribution here for the normal distribution. Now, I got to tell you, this formula for that PDF, forget it. I don't want you to even bother to write it down. I'm never going to use it. But it is defined in terms of E. And there's this square root of 2 pi. Where the hell's that come from? That actually can be answered. That's in Calc 3. Nope. Not just no, hell no, we're not doing that. But that's where this graph comes from. By the way, I can do the CDF. I can build the CDF from that. I can give you a picture of both of them. There it, oops, wrong button. There's our normal PDF. And you'll notice that most of the area involved is within 3 standard deviations on either side of the center. And there's our CDF. It's 0 way out here on the left. As we go to the right, we cover more and more of this area. So the graph sweeps up and then tapers off at 1. As we cover all of the area going from left to right in this picture goes up in this picture. There is no nice way to write a formula for this picture. It doesn't exist. That's why I'm not going to bother. I'm going to simply say the way to do this is to ask the computer to do the calculus for me. Normal.dist, distribution. I need to give it the mean and the standard deviation. I need to give it the x value I want. And then I need to take 0, say I want to do the PDF, or 1, say I want to do the CDF. That's what these last two things are doing. It's just a flag that gets tripped. If you use a 0, you get the PDF values. If you use a 1, you get the CDF values. There isn't a separate CDF command and PDF command in Excel. It just flips that little flag on the end. This is the bell curve we always have. And that's why this picture is labeled without numbers. It's just labeled in terms of the standard deviation and the mean, because they all look the same. So really, I'm going to use this picture every time. I'm just saying, how much of this picture have I covered from here to here? That'll be my probability. How much area is under this thing? But that means I need to do all the calculus to do that. No. I'm going to use Excel. I'm going to use some other program. I'm going to use my calculator, built into here too. Under our distribution button, right here where it says variables, second distribution, right there at the top. Normal PDF, normal CDF. There we go. If I want to use a particular normal PDF, I need to give it the mean, I need to give it the standard deviation. Off we go. It'll draw for me. It'll calculate. If I give it an X value, it'll give me the number. If I want the CDF, there's that one right there. But what this means is that I need to make sure that I'm using this correctly. Please notice something about this distribution picture. This distribution is symmetric around its mean. If we have skewed data, I can't use this. If I have data that is far more to one side than the other, this ain't gonna cut it. So if I'm thinking about the time it takes for you to complete your student evaluation at the end of the year for me, for this course, well, I don't think that's going to look like this. Because some of you will take this in no time at all. I hate it, he sucks, 1, 1, 1, 1, 1. Some of you will be like, no, I'm going to think about this for a while. I have some feedback, I'm going to write down stuff, and I'm going to put it in the comments, and you'll be on this end. But I think this data will be skewed. It may not have a single mode. It may be bimodal. It may be skewed left. A lot of people wrote this very quickly and didn't write very much feedback. Maybe skewed right. A lot of people wrote a lot of feedback. I need to know, am I using this in the correct data setting? Normal variables, height, weight, the amount of water coming out of a bottle in the production line in the Pepsi factory, the diameter of a ball bearing being generated at a particular production line. Those are useful normal variables. I want to not do these calculations by hand. How do I put this to work? That's what we'll cover on Friday. And I'll make my life easier and not deal with lots of different normal curves, but only deal with one of them. Please remember that your Chapter 6 homework is due on Friday. I will see you all then.